Hello everybody. So this video is about this problem statement. Proof that the time complexity of binary search algorithm is order of log n. Okay, that's the problem statement. And for those of you who are software engineers, programmers, mathematicians, computer scientists, those of you who have done a class in data structure, algorithm design, you will have come across binary search algorithms. Okay, so I'm going to prove to you mathematically that the binary search algorithm has a time complexity of log n. In other words, the time to perform search using binary search algorithm is fast. The reason is because if your n is 1000, ordinarily for the sequential search, the linear one, the operation is, the complexity is O of n. In other words, you have to perform 1000 comparisons to look for whatever, to search for items, for particular items. But now, if you take logarithm of 1000, that will give you 3. So in other words, for this particular n, the time complexity of it is going to be what? Order of 3. So now 3 compared to 1000. So this is 3 time steps. While this one is what? 1000 time steps. That's just a rough explanation of why O of log n is faster than O of n. The easiest linear algorithm, search algorithm to understand is what? The linear search, which is O of n. But binary search is a little bit more complex, but not really too difficult. The time complexity of that is what? O of log n. Now let's explain what search algorithm is all about. Okay. And you have an array containing some element, 18, 20, 24, right? Now, ordinarily, number n here, if you count how many numbers you have here, you have 1, 2, 3, 4, 5, 6, 7. Your n is what? 7. Okay? So, if I'm looking for an item, let me call it look for. Or let me call the item, I'm searching for item 20. Now, item 20 is right here. And that is, what is the position of that? If you count, you have how many elements? 7. So this number 20 is at position number 5. Because in most programming languages, the index of elements, you want to assume the first element is 10, but in terms of index notation, you call it index 0, index 1, index 2, index 3, index 4. So the element I am looking for here is item number 20, is also in my list, and the index of 20 is 5. Don't forget, you start indexing from 0. So n element array has indices of how many index? 0 to what? N minus 1. You have to note that, okay? You cannot run from 0 to n. If you run from 0 to n, that means you have n plus 1 items. So that is that. If I want to do all the normal linear sequential search, I'm going to pick 20, number 20, and I'm one by one, I'm going to compare 20 with 10. Is 20 equals to 10? No. Move to the next line. Is 20 equals to 12? No. Move to the next line. Is 20 equals to 14? No. Move to the next line. Is 20 equals to 15? No. Move to the next line. So you can imagine if you have 1 million items, you have to compare term element by element, side by side, all true. So for linear search or sequential search, the time complexity is O of n. So if you have 1 million items, you have to make like almost a million comparison to get what you are looking for. Now I am looking for number 20 in the list. Number 20. And number 20 is right here. So if my number 20 is inside a 1000 element array, and the position of number 20 is 999 or 998. So I have to start from 0, compare with the first one, the second one, the number 100. I have to move through one by one until the location of number 20. So that kind of search is called O of n. It's easy to understand that, but it's very slow. Now, there is a better way out, which is called what? Binary search. Now, the binary search assumes that the array is sorted. In other words, the elements are arranged from smallest to the what? Largest, or largest to the smallest. Okay? That is the assumption of binary search algorithm. Okay, now the binary search algorithm, you are looking for item 20. What you would do normally is you divide the array into two positions, two halves. Okay, call it midpoint equals left plus right divided by 2. So the algorithm starts from here. Remember, I am looking for 20. Now, the algorithm starts from the midpoint because 15 is the midpoint of this array. Now, the algorithm compares immediately if the item is greater than this midpoint. If what I'm looking for is less than this midpoint, the algorithm moves to the left. Okay, but if what I'm looking for is greater than the midpoint, the algorithm moves to the right. So one way is a lot faster. So you divide into 2. Now, if I'm looking for number 20, number 20 is greater than number 15, which is at the midpoint. So it moves just 1, 2, 3. By 3 iterations, I'm done. With only 3 iterations, I'm done. But if I have to use linear search, I have to count from 1, 2, 3, 4. No, it's a lot longer than binary search. Now, how do you prove mathematically that the time complexity of binary search is order of log n? Now, let's go for it. So now, because of the way, the nature of the algorithms, it follows this particular pattern, this particular recurrence relation. And I will explain what that means. You remember, if you have 10 items, you have to divide them into what? 2 parts. First half, second. So what you normally do is you divide into 2 parts. You call this place first half. This is second half. So you compare your item with the midpoint. So if your midpoint is less than your item, right, you move to the right. If the midpoint is greater than your items, you move to the left. So it's faster. That is the reason for this Tn equals T subscript n equals Tn over 2 plus alpha. That is the recurrence relation that describes the operation. Now, the n and alpha here, both are integer numbers, but your n should be greater than or equals to 1. Your alpha can be greater than or equals to 0. Okay? That is the condition for that. So you know the n is number of items. N is what? Number of items in array. Okay, now that means your Tn, if you work on this n over 2, your n over 2 becomes n over 4 plus alpha, then plus this alpha here. See? Again, your Tn over 4 becomes Tn over 8 plus alpha, plus this alpha, then plus this alpha here. You continue that way, your Tn over 8 becomes Tn over 16 plus its alpha here, then plus alpha here, plus alpha here, plus alpha here. That's how you continue. Now, remember at the left side here, you have your Tn. Okay, so generally, if you discover that your Tn here is Tn over 16 plus 4 alpha. See that? Plus 4 alpha. And this is the same thing as T n raised power 2k 24 plus 4 alpha. Right? Now, if you have 4 here, you must have 4 here. So generally speaking, if you have k here, then you must have k here. See that? Now, and the objective is that we will move from Tn down to T1 until you look for your items. N is the number of iterations to perform until you stop, until your n becomes 1. So essentially, I am looking for this right side to be 1. You see that? That means n all over 2 raised power k must be 1. Why 1? 1 is when I will stop, right? Because you have to reduce it. If you have 1,000 items, you have to search until what? No more item to search until the last item when your n is 1. When your n is 1, that is the last items. So you want to make sure the subscript at this right hand side becomes 1. You started from what? From this. You must understand this relation based on the nature of the algorithms, and you have to go that way until the subscript at the right hand side is 1. That means your n over 2 raised power k equals 1. That implies n equals to 2 raised power k. And this is an exponential expression, so you can introduce logarithm to both sides. That is log 2 raised to the power k, right? And that means k equals, no, that means log n equals k log 2. You see that? And that essentially means that your k is log of n over log of 2. Now, log of n divided by log of 2 actually means log n base 2. Now, this k, if you look at the k here, k actually will represent your number of iteration. Look at when we started from the first, this is the first one. For the second one, I have this. So that's 2 raised to the power 2. That's second iteration, 2 raised to the power 2. And for the third iteration, I had 8 here, which is 2 raised to the power 3. So k is 3 for the third iteration. And for the fourth iteration, I have n over 16. That is 2 raised to the power what? 4. So your k is what? 4. Fourth iteration. Now you have to continue that way until you have this, as I've explained before. Look at that. 4 alpha. So generally, when you had n over 16 here, that is n over 2 raised to the power 4, right? Which is and the 4 here, you have 4 here and 4 here. Now, if you have, generally, if it is 4 here, you can replace this power by k and k, okay? And the target is to make sure n over 2 raised to the power k equals 1, right? Because you have to move from tn to what? Until t1. T1 is the last item once again. So n over 2 raised to the power k equals 1. So this circle here must be equals to 1. And then you have that. So okay, and this can be written as, if you want, again, you can write this as what? 1 over log 2 times log n. Now, in asymptotic complexity, you ignore constant. This is a constant. So you ignore that, and that comes down to what? Log n. So your k is actually log n. Now, k, once again, k is what? Number of iteration, right? Or operations. Now, let me call it number of operations. So your k is log n. So for n elements array, the number of operation is log n. That means the number of operation is fast. And you can write this as what? Order of log n. Order of log n. You see that? So the time complexity of binary search algorithm is what? O of log n. Remember, sometimes if you have a nested for loop in C++, if you have for int I equals 1, I less than or equals to n, I plus plus, and then you have another loop for int j equals to 1, j less than or equals to n, j plus plus. Now, if you are doing C out I plus j, right? And you close this inner for loop. Now, for this nested for loop, the number of operation is going to be, because you are moving now. If you have this array, so the number of column is 3. The number of row is 3. So you have to consider all the items 3, 4, 5, 6, 7, 8, 9, which is order of 3 square. So if this is n, this is n. So for nested for loop, the order is what? O of n square. I'm just explaining that. Now, the order doesn't mean anything special. It just means that the number of operations that you will perform is going to be what? N squared. And for binary search, once again, the time complexity is what? Order of log n. That is how to prove it. Once again, look at it from the beginning. And I hope this is very, very informative. Thank you, and have a good day.